Welcome back all of you. In the last lecture, we have finished this module 3 and we have discussed various aspects of stress path. In this lecture, we will work out some representative problems related to stress path. So, the first question is, a soil sample is isotropically consolidated to sigma naught dash. There is no cohesion and angle of failure line is alpha. Slope of effective stress path is beta for over consolidated state of the soil and that is in compression. Prove maximum shear stress at failure Tf is equal to sigma naught dash tan alpha upon 1 minus tan alpha by tan beta. So, this is a representative problem which help us to interpret the question and draw the stress path. There are a few conditions which are given and the most importantly it is over consolidated. Alpha means it gives a clue that it should be in TSS dash plot. There is no cohesion, so A dash is not going to come into picture. So, it is first it is isotropically consolidated, that means we know where is the starting point and we need to first find out what is the slope of ESP. Okay, so, effective stress path, so it has to be in a more general manner. Had it been total stress path, we know like there are clear specific leads, 1:1 is the slope, but since it is effective stress path, we also need to take care of other aspects as well. Now, let us try to solve this problem. So, it is clear that it is on TSS dash and the slope of the failure line is alpha. So, that is marked here. The next is the initial point. A soil sample is isotropically consolidated to sigma naught dash. So, it gives a clear indication that it has to be on the isotropic line, and which is the isotropic line? So, this is the isotropic line. So, the initial point, that is P dash, which corresponds to sigma naught dash, will be here. Now, how does this point become sigma naught dash? Because we know that S dash is equal to sigma naught dash plus sigma naught dash by 2. Why is it so? We know that S dash is equal to sigma A dash plus sigma R dash by 2. So, since it is isotropic, sigma naught dash plus sigma naught dash by 2, that will be. So, S naught dash, that is the initial point, S naught dash is equal to sigma naught dash. Now, how did I draw the effective stress path with such an inclination? Now, nothing is told, only thing is it is told that the effective stress path is at an inclination of beta. Now, this beta can be in this direction as well. So, how did I plan to draw ESP in this direction? ESP in this direction. Now, we have to look back to the slope of ESP in TSS dash plot, that is 1 by 1 minus 2A. Now, for over consolidated state, the A value at failure, if that is to be considered as constant, let us take AF to be constant, and we know that for heavily over consolidated soil, AF will be negative. So, if you substitute for A equal to a negative value, whatever be the value, this whole of the slope will become positive. So, we are sure that for OC state, this ESP is going to be positive, and that is what I have drawn with a positive slope, and that is equal to beta. And what is the maximum shear stress at failure? This is the maximum shear stress at failure, because where effective stress path touches the failure line. Now, this is TF, and now the problem is very simple. The only aspect we need to keep in mind while solving stress path problem is that we should be able to plot it correctly. Once we get the geometry, then it is very easy to solve the problem. So, what is important is to determine the slope the certain basic knowledge that failure is always brought about by effective stress path. So, these bare minimal conditions we should keep in mind, and that will help to solve the problem. Okay, now the problem is simple, it is only geometry now. Let us consider this distance to be b. So, tan alpha, considering this particular triangle, tan alpha is equal to Tf divided by, this is sigma naught dash. So, this distance is sigma naught dash and this distance is marked as b. So, that is sigma naught dash plus b. Tan beta, this triangle, we have Tf by b. So, that is what is written here. Then I can replace b. So, tan alpha is equal to Tf upon sigma naught dash plus Tf by tan beta. Now, further rearranging, we have sigma naught dash tan alpha plus Tf by tan beta into tan alpha equal to Tf. Taking Tf to one side, you can write Tf, we will take it outside, 1 minus tan alpha tan beta by tan beta, which is equal to sigma naught dash tan alpha. So, Tf is equal to sigma naught dash tan alpha upon 1 minus tan alpha tan beta, and that is what is the expression that we need. So, hence it is proved. Okay, this expression you can use it for solving further problems as well. Okay. So, that is all about the first problem. Now, let us move on. So, the next problem is as follows. There are two cylindrical samples A and B. Now, both the samples were isotropically loaded by a stress of 200 kilopascal under drained condition. So, there are two samples A and B. Let us consider it to be a triaxial sample. Both of them are isotropically consolidated. So, isotropically consolidated, it is very clear that it is under drain condition, otherwise it will not consolidate. And the initial isotropic consolidation pressure is given, that is 200 kilopascal. Further, let us take the case of sample A. For sample A, radial stress was kept constant. Radial stress means sigma r is kept constant and axial stress is increased to 440 kilopascal under undrained conditions. Now, you remember that it is a straightforward case of compression. So, radial stress was kept constant and axial stress increased by 440 kilopascal, and now we have to keep in mind that it is under undrained condition. For sample B, axial stress was kept constant and radial stress reduced to 50 kilopascal under drained condition. So, this is also compression because axial stress was kept constant and you are releasing or reducing the radial stress. Now, earlier radial stress was 200, it is reduced to 50 kilopascal under drained condition. Now, that also we have to keep in mind. Now, we need to plot total stress path and effective stress path in QPP dash plot for A and B, assuming soil to be linear, isotropic and elastic material. Calculate maximum excess pore water pressure for sample A. So, it is a straightforward problem. We are not asked to find out any failure conditions, rather we just need to find in what manner the total stress path and effective stress path would be in this particular problem. So, let us say A and B is isotropically consolidated to 200 kilopascal, and before that I think we also need to take the value of A parameter, that is the pore water pressure parameter also. So, we will do that or we will assume that in the due course. Okay. So, A and B is isotropically consolidated to 200 kilopascal. So, P dash is, we need to find out what is the value of P dash and Q dash, because that is where we have to plot it, and delta Q is equal to delta sigma A dash upon minus delta sigma r dash. So, this is known to us. So, the initial condition is 200 plus 2 into 200 by 3, this is 200, and delta q is 0. Let us plot this initial condition. So, we are starting from 0, we are consolidating it isotropically. Here you can see q is same. So, delta q is 0 and delta p dash keeps increasing to 200 kilopascal. So, this is p dash because it is isotropically consolidated. There is no pore water pressure existing in the beginning. Okay, so, that is 200 and this initial point is p dash. Here effective stress path is equal to total stress path, and these things are very clear to all of us. Now, specifically for sample A, let us start, it is an undrained condition. Undrained loading, we know that it is at constant radial stress. So, delta sigma r equal to 0. So, interpreting the question is very important. Delta A is then increased to 440 kilopascal. So, delta sigma A will be 440 minus 200, because earlier there is an isotropic stress condition further which it is increased up to 440 kilopascal. So, do not misinterpret that 440 is in addition to 200, it is increased to, the axial loading is increased to 440. So, the total axial stress increment will be 440 minus 200, which is 240 kilopascal. So, these data is known. Now, for total stress path, it is pretty straightforward. Delta P is equal to delta sigma A plus 2 delta sigma r by 3. Now, delta sigma r is 0, that is substituted, delta sigma A is 240 and hence delta P is equal to 80 kilopascal. Where you can go wrong in this question, if you interpret that it is 440 is over and above, there is a possibility of misinterpretation. In fact, it is loaded to the final value. So, those terminologies and English usage you have to keep in mind. Delta Q is equal to delta sigma A minus delta sigma R, which is 240 minus 0, which is 240 kilopascal. Delta Q upon delta P is 240 by 80, which is equal to 3. Now, this slope we already know. In Q, P, P dash we have already seen for drained condition, that is total stress path equal to effective stress path, the slope is equal to 3. Now, in the undrained case, for total stress path, this slope will always remain same. So, that is what we have just found out, and that is equal to 3. So, this is PQ is the total stress path at an inclination of 3 or a slope of 3. So, here this value will be 280 and 240. Now, the final value will be, because this is delta P. So, increment is 80. So, here up to here it is 200 plus 80. So, that is 280 on x axis, and y axis which is represented by delta Q, which starts from 0. So, whatever it is 240, that appears as 240. So, this is the point Q. Now, we also now need to find out what is ESP. So, the moment for undrained case we need to plot ESP, we also need to determine what is the variation in pore water pressure. So, delta U is the excess pore water pressure, which is B into delta sigma R plus AB delta sigma A minus delta sigma R. B is equal to 1 and delta U is equal to 0 plus 1 by 3 240 minus 0, which is equal to 80 kilopascal. Now, what is the catch here? It is already given in the question. Assume the soil to be isotropic and elastic. Now, if Skempton's pore water pressure equation for triaxial condition is not clear to us, it is difficult to assume the value of A. Here, for elastic condition, we know that the value of A is equal to 1 by 3, and that is what we have done here. A has been substituted to 1 by 3. So, delta U we will get to be 80 kilopascal. So, this is the condition that we have used. So, slope of effective stress path is equal to, this also we know, 3 divided by 1 minus 3a. Now, a, the value is 1 by 3, so here it becomes 0 and hence it will be infinity. So, that means it goes vertically upwards because it is delta q upon delta p. So, delta p there is no change, there is no change in p. So, it has to go vertically upwards. Delta q is equal to delta q dash is equal to 240, which we have already seen in the previous slide. Okay. So, maximum value for this particular case is 240. And delta is, so q dash, I have just taken q dash just to make sure that it is for effective stress path, but we already know q dash and q are the same. So, q dash is equal to q naught plus delta q, that is 0 plus 240. So, it will be delta p dash is equal to delta p minus delta u, which is 80 minus 80, which is equal to 0. So, that is also now known. So, there is no change. So, p dash is equal to p naught dash plus delta p dash, that is 200 is the initial value plus 0, which is 200 kilopascal, and hence delta q dash upon delta p dash equal to infinity, and this information we already have here. Is just for your understanding, we have worked it out. So, here is the effective stress path. So, this we have understood. Now, this is q dash 200 and 240. Now, what is this distance? It is already there, delta u, which is equal to 80. So, 280 minus 80, that gives 200, q value is 240 as we have determined here. So, that is all about sample A for undrained loading. Now, sample B. So, we know that it is a drained unloading. So, here it is release of radial stress. So, it is unloading. So, drained unloading, delta sigma A is 0, axial stress kept constant, sigma r decreased to 50 kilopascal. So, there was an initial value of 200, from there it is decreased to 50 kilopascal. So, delta sigma r is equal to 50 minus 200, that is minus 150. All these sequence of loading we have clearly discussed while discussing the stress path. So, you can cross refer to those for understanding this better. So, TSP, now TSP and ESP both are same because it is drained unloading. So, delta P is equal to delta sigma A plus 2 delta sigma R by 3, delta sigma A given 0 plus 2 into minus 150 by 3, it is minus 100 kilopascal. Delta Q is equal to delta sigma A minus delta 0 minus of minus, it is plus 150. So, delta Q upon delta P is equal to 150 upon minus 100, which is equal to minus 1.5. Now, so it is very clear that the slope is negative. P is equal to P naught plus delta P. So, P naught is 200 and delta P is equal to minus 100. Substituting that, we know that it is 100 kilopascal, but in the leftward direction. And Q is equal to Q naught plus delta Q. Q naught initial value is 0 plus 150, delta Q is plus 150, that will give you 150. So, 150 in this direction, 100 it has to go in this direction. So, that is the slope, it is negative slope. So, TSP for B. So, that is all so this is the PR is the required TSP for B, and all other interpretation it comes from this calculation because it is minus. So, we know that it is moving in this particular direction, and apart from that the slope is also minus. So, we know that it has to be in the leftward direction. Now, should it be in which direction, that should it be in this or in this. So, that information you will get from the actual values of P and Q. Okay. Here it is looking positive, but please remember that it is going in the reverse direction. The earlier value was 200, since it is negative it is decreasing. So, we know that in which direction it will be moving. Okay. So, that is 100 and 150. So, ESP of this delta U is equal to 0 drained. So, Q dash is equal to Q naught plus S is 150, P is 100 kilopascal, and hence it is the same. So, there is no difference for ESP and TSP. So, since it is drained, we do not have to explain it further. So, that is all about the second question. We will move on to the next one. Okay, so the next question is, an embankment is to be constructed on soft clay as shown. So, this is the embankment. The top width is 11 meter, bottom width is given, it is 17 meter, the height is 2.75 meter, and the bulk unit weight of the material is 20.6 kilonewton per meter cube. And this is the soft clay below with the given properties. There is a water table at 1 meter depth. Above the water table, gamma or the bulk unit weight is 12.1 kilonewton per meter cube. Below the water table, the saturated unit weight is 12.7 kilonewton per meter cube. Initial water content is 140% below, liquid limit is 160 and plasticity index is 105%. And the lateral earth pressure at rest K naught is 0.6, that is given. A parameter before failure is 0.35 and A parameter, that is AF, at failure is 0.5. So, Skempton's A parameter is given. Triaxial compression test in the lab, you can add, gave the effective friction angle equal to 23 degrees and C dash equal to 0. Determine whether the soil element at depth 5 meter would fail or not. So, this is the reference soil element which is at 5 meter below the ground surface. Now, we need to understand based on stress path whether this particular element would fail or not. Consider the vertical stress increment at 5 meter depth is 0.9 times at the ground surface and lateral stress increment is 0.33 times of vertical stress increment. What is the importance of last statement? So, there are two cases. First is the initial condition which is due to self weight. Now, under self weight it is not going to fail. Now, when you are placing the embankment load, whether the element would fail or not, that is the question. Now, when you add the embankment, there will be some amount of stress that gets added up at the element A. Now, if you study the stress distribution, we know that there is a way by which we can calculate it. Here, we are adopting this particular information for finding out what will be the stress increment at point A. That is, consider the what it is at 0.9 times. Now, if you consider what is the stress because of this embankment at the ground surface, then at point A it will be 0.9 times of what is the stress due to embankment at ground surface. So, first we need to find out what is the stress increment due to embankment at the ground surface. Its 0.9 times will be the stress at the element A, and the lateral stress increment is 0.33 times of vertical stress increment at A. So, those information are given. So, let us see how to solve this problem. So, initial condition of A, it is because of the self weight. So, sigma V naught is equal to 12.1 into 1 plus 4 into 12.7. So, that is the total vertical stress which is equal to sigma 3 kilopascal, and that is the initial condition. U naught, if you consider a piezometer here, it will rise up to 4 meter. So, 4 into 9.8 which is 39 kilopascal. So, sigma V naught dash is equal to 63 minus 39, it is 24 kilopascal. So, sigma H naught dash is equal to 0.6 because lateral earth pressure at rest is given to be 0.6. So, 0.6 into 24, that will give us 14 kilopascal. So, sigma H naught is equal to 14 plus 39, that is the total horizontal stress, 14 plus 39 which is equal to 53 kilopascal. So, initial condition is known. So, T naught, we are plotting this in TSS dash plot. So, we can find out what is T naught, which is sigma V naught minus sigma H naught by 2, all the values are given 63 minus 53 by 2 which is 5 kilopascal, S naught the same plus 63 plus 53 by 2 which is 58 kilopascal. So, the initial condition is now known. So, S naught dash is S naught minus U naught which is equal to 58 minus 39 which is equal to 19 kilopascal, because U naught is 39. So, all these initial conditions are known now. So, TSS dash, KFC is the failure line, and you can easily denote what is KFC because phi dash is known. Tan alpha is equal to sin phi dash is 23, so we get 0.4. So, sin 23 equal to 0.4 is the slope of the failure line. Without this, this problem cannot be solved. Now, the starting point is the point P. We know that it is T naught and S naught, which is 5 and 58. So, here it is somewhere 58 is the S naught and T naught is 5. So, 58 and 5. We have S naught dash, which is S naught minus U naught, that is P dash is around 19 kilopascal and T naught remains same. So, at 5 height we have 19. So, it is close to here 19. So, P dash, that is 19 5. So, it is, you can see that the initial point itself is very close to the failure line. So, you can make some judgment right at this point itself, like there are not much of allowance for failure, like it is very close and factor of safety is substantially low. So, factor of safety, how do you, in the last lectures we have seen that when it is close to the failure line, the factor of safety is less. So, accordingly we can easily make out the factor of safety, or the safety margin is quite less in this particular case. This is 39. Okay. Now, after the construction of embankment, what will happen, whether it was going to fail or not. So, the incremental stress is delta sigma V, which is equal to 2.75, which is the height of the embankment, into 20.6 is the unit weight given for the embankment material, which is 57 kilopascal. At 5 meter depth, what is the entire stress is not going to be delegated, it is 0.9 times according to what is given in the question. Delta sigma H equal to 0.33 into 51, which is equal to 17 kilopascal. So, this is given and this is as per what is given in the question. Now, delta U, what will be the change in pore water pressure because of embankment construction? It is B into delta sigma H plus AB into delta sigma V minus delta sigma H. Substituting this, we have all the information with us. We have delta U is equal to 34 kilopascal. So, sigma Vf is 63 plus 51, the incremental load, that is 114 kilopascal. Sigma Hf is equal to 23 plus 17, which is 70 kilopascal. Now, with this we can find out what will be the final condition of total stress, that is Tf is equal to sigma Vf minus sigma Hf by 2, which is 114 minus 70 by 2, which is 22 kilopascal. So, here it is 22. I am drawing a dashed line here. What is SF? SF is equal to sigma Vf plus sigma Hf by 2, 114 plus 70 by 2, which is 92 kilopascals. So, somewhere here. So, I am drawn a vertical dashed line. SF minus U naught, that is 92 minus 39, which is equal to 53. So, we already know that it is 39, which is 53 kilopascal. So, UF is equal to 34 plus 39, because in the previous slide we have seen that delta U because of embankment construction is 34. So, initial is 39. So, total pore water pressure at final is 73 kilopascal. Why did I use this particular SF minus U naught? This is to just show that the total stress path here is translated to a total stress path here, that is TSP minus U naught stress path. So, T minus U naught stress path. We have total stress path TSP, and from the total stress path whatever is the initial pore water pressure we minus that, so that we draw the total stress path at this particular point. So, that is another way of representing total stress path, T minus U naught stress path. That also we have discussed in the last lecture, you may please refer back. So, S dash F is equal to SF minus UF, that is 92 minus 73. From here you need to minus the final pore water pressure 73, that is 19 kilopascal. So, it is at the same point here, S dash F is at this point. So, this is the total stress path PQ, that is 92 22. So, this is 92 and here it is 22, that is due to the construction of embankment. Now, when the embankment is getting constructed, the total stress path is progressing in this direction, and that is 92 22, that is total stress path. Now, this is T minus U naught stress path. It is parallel to stress path, but it is drawn at this initial point, and that is initial pore water pressure 39 is minus from this, and this is the T minus U naught stress path. Now, the effective stress path is the S dash F is 19. So, it is at this point, and what is TF? It is 22. So, it moves in this direction and touches here. Why it is moving in the vertical direction? It is already given in the question that the final pore water pressure at failure will be the A parameter corresponding to this will be 0.5, and we know that the total stress effective stress path of TSS dash plot is 1 by 1 minus 2A. Okay. According to that, that is slope is 1 by 1 minus 2A. So, AF is given as 0.5. So, if you substitute AF equal to 0.5, this will be infinity. So, that is why it is moving vertically upwards. So, that is what is shown here, AF equal to 0.5, and that gives infinity. So, it is in the vertical direction, and this is 1922. Now, we do not need to discuss further to say whether it will fail or not. Yes, the stress state according to the final construction of embankment is well above the failure line, which is an impossible state. So, the soil would have failed by the time it reached here. It cannot cross the failure line in any circumstances. So, the embankment construction would fail the soil element which is at 5 meter depth. So, ESP indicates the failure of soil element. So, how beautifully the effective stress path helps us to understand a lot of facts, whether it will fail, at what time it will fail, and how it is going to fail. All these information we can derive by plotting stress path. So, this is a very good example which clearly demonstrates for a field problem how we can interpret various situations based on stress path plotting. So, now whatever we are asked to find out, it is already done. We have found out what is the excess pore water pressure, we have found out whether the embankment construction would fail the soil element or not. All these things are known. Now, we are curious to find out what is the possible strength available if the condition is to be safe. So, the strength available, that is TFS corresponding to S dash F, because this is a starting point, is equal to 19 kilopascal. That is S dash F equal to 19, that is this particular point. What is the available strength, that is TFS. So, this is what is shown as TFS. Now, TFS is equal to, we know that the inclination is 0.4 into 19 this distance, that is 7.6 kilopascal is the strength available here. So, maximum shear stress increment which is possible due to the construction of embankment if the soil has to be safe is equal to 7.6 minus 5, which is equal to 2.6 kilopascal. So, 2.6 kilopascal is the only permitted increment. Why it is 2.6? Because we know that AF is 0.5 and it is moving in the vertical direction. Now, if it is moving in the vertical direction, the only possible increment available with us is 2.6 kilopascal. So, we can construct only that much of the embankment that will give an incremental stress of 2.6. Beyond that, it is going to fail. So, we have understood like where it is going to and how it is going to fail. Now, here already the initial condition is at 5 kilopascal above. Now, let us say that if it is isotropically consolidated, then we would get an allowance of 7.6 kilopascal before failure. That is, this point will come down. So, total possible increment would be 7.6. It is only an added information which we can get from the stress path plot. For example, if the starting point is again towards left, we will have even less allowance, or if this point is slightly here, then we have this much of strength available. So, that much amount of embankment construction is possible. So, this particular plot help us for various possibilities and understanding related to a given field condition. This is what we have discussed related to embankment. Now, this can be any problem, it can be a foundation, it can be retaining walls like the one we have discussed in the last lecture. So, that is all. So, now we have almost completed module 3 and some representative problems we have done. The problems which are discussed in this lecture, these are very similar to the one reported in the textbooks of M. Buddhu, Halls and others. Okay. So, please refer to these textbooks for more examples. So, that is all for now in this lecture. The last lecture in module 3 is summarizing the whole of module 3 what we have learned. So, that is all for now. Thank you.